Welcome back, everybody. I'm Jolene Moon. You've landed on my Science is Magic YouTube page where I talk about the science and maths that fascinates me, and this is my second week final video of my Minecraft and chill revision series. This is the chemistry video. Check out my maths and physics videos that have also released. We are building a base. I've finished in the end. I've gathered some resources, and I'm now building and working on this new project, which I think is going to be pretty fun. I'm hoping by the time I get partway through, people will start to recognize what I'm attempting here. Anyway, today's videos have a theme of mistakes, misunderstandings, and other general musings about GCSE science. And what we're going to do is just have a chat. I'm going to be covering a little bit of specific revision advice, but otherwise just chatting about mistakes that I made in the hope that it might help other people learn. So do what you've got to do, grab a cup of tea, chill, maybe absorb the revision advice while I entertain myself with some Minecraft. Now, I did talk about some mistakes I used to make with chemistry in my physics video, but the biggest one by far was thinking that chemistry was easy. And oh my goodness, it's not. Particularly organic chemistry. Organic chemistry has kind of been the bane of my education. It just it escalates quite quickly, is what I'm trying to say. It gets pretty complicated. Understanding reaction mechanisms and all the different behaviors of the molecules at A level really gave me headaches. And at GCSE, it's confusing because there's a lot of information to take in, and it's all kind of brand new. You learn about all the different functional groups. You learn about all the different names and the counting and the structures of those molecules. My best advice is to really separate them out and really recognize them and get familiar with them. Study, memorize them. It's really the only way around it to build a solid foundation to improve your understanding of organic chemistry. So first things first there. Whereas I thought physics was hard and chemistry was easy, and I would actually say in retrospect, because as soon as I moved on to my A levels, chemistry became wickedly hard. Whereas I just enjoyed reading about physics so much. I enjoyed so much improving my understanding of the fundamental forces, the quantum effects that improved my understanding of just energetic behaviors, particularly with electrons, as I mentioned in my last video. It was a delight doing my physics A level, whereas chemistry really gave me a headache. So do not underestimate this course, or this section of your GCSE if you're doing the combined or double science. Anyway, second biggest mistake was underutilizing the periodic table. Now I've done a short already about the periodic table, but I will be doing a deeper dive into the periodic table because I love it. I love the idea of silly little guys all over the world in ancient times, older times, just measuring little bits of powders, grinding up metals and rocks into powders, and then weighing them and being like, where does this go on this chart that I've made? It's so goofy and funny, and just humanity's incessant need to categorize everything, and compare and contrast things. And I don't know, I think it's adorable. That's probably really weird to say, but anyway, the periodic table exists the way that it is and does what it does for a very specific reason. And I did not appreciate that in my GCSE, is all I'm saying. And again, that's one of those things, like I said already, that you appreciate when you do the A level in science. You appreciate so many things that were just not, because you're really taught the basic. I understand there's a reason for that. You've got to learn the foundational simplified stuff, but then you basically get to A level and it's like, okay, disregard everything you thought you knew. We're basically starting over. You have a foundational understanding. Now let's actually correct that. It's like, I think, someone who cannot draw, so someone like me, trying to draw a sketch of a person, and then a professional artist, like my partner, coming along and being like, okay, I see what you were trying to do. You drew like a sphere for the head or a circle, and you vaguely got the body shape right, but it looks silly. It looks not even cartoonish, because cartoons are drawn in really specific ways to evoke certain body shapes and motion. So the professional artist might come along and sketch in and add in the detail and like correct the shapes to evoke motion. I'm just gonna lay out a palette here, don't mind me. And I think understanding science and improving your science education is like that process of improving art. And it's kind of like, okay, I understand that you were doing the circles and kind of trying to get the shape right and trying to freehand all the silly shapes, but here's how you actually do that properly and fill in the details from the beginning, knowing where you're going with the sense of the 3D, the shapes and the motion. Anyway, total tangent. That's the musings part of the video. So things like relearning definitions, relearning the fundamental understanding for a concept. And I feel like the periodic table is one of those things, because you've got to learn the trends and the patterns in the periodic table, but you're not really told why you have to learn that. And the reason is because the chemistry is all about electrons. It's all about electron behavior and how that creates effects and reactions on a macroscopic human level. Where you put two liquids together and they go bang, and how do you make that not happen? How do you get the liquids that you want to mix together, or the powders, whatever. And the periodic table is your map to understanding what electrons are going to go where and what is going to do what and why they will do that. So that's why you have to learn the patterns and the trends, because you're literally doing the explanation part. But it's kind of like then at A level you have to go back and relearn all of that and be like, oh, that's why that did that. Oh, so I have to say this is why that happens, rather than because it's in group 1 and it has one electron in its outer shell. It's like, oh, it's trying to become stable, and it's more energetically efficient or effective to emit the electron rather than try to absorb things. So that kind of thing. Anyway, just an example. And similarly, not learning proper definitions, full stop, hindered my grades. The chemistry, I think I may have even talked about this last week. The chemistry mark scheme is highly specific. You need to know and you need to say exactly what they want you to say, because if you put a wrong word or you even spell something wrong, or I think they tend to be lenient with most spellings, apart from in the questions where they indicate you will be marked on your spelling and grammar. Apart from those ones, you have to say specifically what they want you to say. And I just did not appreciate that. I only learned that through trial and error. So, word to the wise. Another thing is, not specifically me, this is kind of, I said I would talk about my mistakes, but as a tutor I've noticed a lot of, so this is I'm kind of changing topic here. So there's what the mark scheme wants you to do, and then there's what the question is asking, and a lot of people struggle to connect the two, and I totally understand that. I had the same issue. But if you understand what a question is actually asking you to do, or what the point of the question is, without them explicitly saying it, very powerful stuff. That's the stuff that's going to get, that kind of thing of being like, oh, I understand what this question, I understand what topic it falls into, I understand what understanding what learning objective I'm demonstrating by answering this question. I know what I've got to do, and you just get on with it. So that, if you're missing that, you will struggle, and there's a specific point to being told, write an equation for the reaction of blah 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 with blah blah blah, and make sure it's balanced, right? And you've got to learn how to balance equations, and that's the whole thing. But when people are like, so say we're going to mix a metal oxide with an acid and we'll see what happens, write down the products that will form, or here's an acid, here's a base, write down the products that will form. people don't really seem to appreciate that there's a pattern to these things, and this is why it occurred to me in my brain, because I was just talking about the patterns and trends of the periodic table and why it's so powerful. You don't need to guess what reactants are going to form, like what products reactants are going to form. It's not random. There's no guesswork needed. If you understand the patterns and structures of what's going into the chemical elements and compounds that are reacting, you'll know exactly what products are going to form. And this is why, like, one of the biggest ones that you learn at GCSE is acid plus base goes to salt plus water. And that's one of those big overarching patterns that chemists, aim to explain and understand in depth. So if you understand what bonds with what in the periodic table, metals with nonmetals, acids with bases, group 1 and group 7 are best friends. Why is that? Those kinds of things. It won't be random and it won't be guesswork, and you'll be like, oh, I understand the pattern of what does happen when you mix a metal oxide with an acid. Do you guys know? It's not, well, I'll leave it. I'll do a video about that this week, so check that out if you don't know. Check back in for that revision. Anyway, moving on. The other thing, and I was going to talk about this in my physics video, but I kind of skipped over it, and the mistake was not utilizing units. And teachers will tell you constantly, and I will tell my students constantly, remember your units, quote your units, what units is this in? And it might feel like it's arbitrary, but it's not. And when I corrected this mistake of just ignoring and not bothering with units, because I was like, well, you say don't forget your units, write down your units, but the questions where they say add in the units are so rare. Most of the time they just give you the units, so it doesn't really matter. When it matters is when you've got mixed units in questions and you've got to convert units. The amount of students that forget to convert, like liters, milliliters, centimeters cubed and decimeters cubed, confusing and not converting these properly all the time. 1 liter is 1000 milliliters. 1 centimeter is 1 milliliter, and centimeters to decimeters has the same 1000. You've got to multiply or divide depending on which way around you're going. That was probably a very confusing way to say that. Make sure that you divide your centimeters by 1000 to get into decimeters cubed, right? Now, the next thing is, I was still talking about units and equations. So N, M, and MR, and N, C, and V. Now, if you've been doing some chemistry revision already, you'll know exactly what I mean by that. I'm talking about the mass, moles, and molecular or relative molecular mass, and the moles, concentration, and volume equations. And these used to endlessly frustrate me because it's not an equation. So in physics, we do the equations, a lot of them, in maths, and it's quite straightforward. In chemistry, you've got to understand the mole to understand these equations. And again, because I was dismissing units all the time, I really struggled, and it took me a lot of practice to really understand what was going on with these equations. And I managed to turn this mistake around when I realized that if you understand what the units are doing, you will always know which way round to multiply or divide just by checking the units. Because if you've got a certain amount of grams of stuff, and then you've got a certain amount of moles of stuff, and you're trying to find the grams per mole, it's the grams per mole. So you divide the grams by the number of moles. Easy peasy, and then all the logic falls into place, and that works for any equation. Understand what the units are doing, or just look at what the units are doing, and that tells you what way around the equation goes, and you don't have to worry about it. Obviously, not all of the quantities have those units explicitly connected like that, but a lot of them do, and you can get away with not needing to worry about a lot of equations with that little skill. So anyway, now we will move on to some misunderstandings. The Chatelier principle. Let's talk about the Chatelier principle, or the Le Chatelier principle. So what we're talking about here is equilibrium. When when reactants are approaching chemical equilibrium or dynamic equilibrium, they're approaching a steady state where the forward rate is equal to the backwards rate, because so this only applies to reversible reactions, and we can go forwards or backwards, and the rate at which the forward reaction occurs will not necessarily be the same as the backwards rate until they get to the point of equilibrium where they're just going forwards and backwards, like one of those Newton's cradles. I was going to call them ping pong balls, you know, the little metal balls that go tap, 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 just backwards and forwards like that at steady state. Whereas when you first put chemical reactants together, you'll get a rush of reactivity. It'll go, you know, depending on the activation energies and things. It'll either zoom ahead and go, or it'll be a slow build-up. But eventually it will slow down because the backwards rate is catching up and it's starting to go backwards. And then they will eventually approach an equilibrium where they're going at the same rate. Now, I used to always confuse that with the quantity. I used to think that that meant you've got like 100% reactants, and then if the reaction only went forward, it would be 100% products. But because we've got this Chatelier principle thing happening, it means you've got 50% a soup of your reactants and 50% a soup of your products. That is not the case. And again, this is one of those things that you learn in more detail at A-level, but let me tell you retroactively, there are ways of calculating the amounts at equilibrium, and it's to do with lots of other reaction constants and things that you learn in A-level chemistry. But at GCSE, all you need to know is that it's the rate. Always when you're talking about equilibrium, talk about the rate of reaction, not the amount of reactants, right? The amount could be whatever. You might need to use up 95% of your reactants before the forward and backward rates are going the same. So you've only got 5% of your reactants left, right? If that doesn't make sense, let me know, and I'll do a video explaining Chatelier's principle. But anyway, moving on. Now, well, power laws and rate equations used to confuse me. So we can connect this to speed, distance, time graphs, where the reaction rate of an order 0 or a first order or a second order reaction is kind of analogous to distance, velocity, and acceleration, because you have, if the rate of reaction doesn't depend on the amount of a reactant, that's kind of like when you're just going at a speed and not accelerating, or kind of like staying at a constant speed and increasing your distance. Right? There's no rate of change depending on the reactant there. Whereas first order law, the more reactant you have, the more you will increase the speed. That's a linear proportional relationship. That's very intuitive to understand. I think it's the 0 and the second order which are harder to understand. So the 0 is like the constant speed regardless, and the second order is where it's non-linear. It's being affected by other things. So that's like the relationship between distance and acceleration, or when we've got an increase, actually a rate of change in our acceleration where we don't have constant acceleration. And if I've just made that even more confusing, I apologize. But if you understand speed, distance, and time, you do also understand rate of change in chemical reactions, because it's the same maths, it's the same logic. Yeah, so maybe let's move on from there to a slightly simpler one, which is the difference between giant ionic and giant covalent structures. And I still, even now, sometimes if I'm not thinking about whether something is ionic or covalent, and I just know that I'm dealing with a substance, especially if it is crystalline or ordered in any way, and I'm not thinking about what the chemical bonding is, my brain will immediately just lump them together. But they are very, very different, obviously, fundamentally different. Ionic versus covalent, not the same at all. And the difference, obviously, is that bond. It's whether you've got static, electrostatic attraction holding the substance together and creating a repeating unit of the spheres essentially just stuck together, versus the covalent bonds where you have actual chemical overlap of electron shells and electrons whizzing around both rather than separately. But the structures that forms wildly can be really similar. So I'm thinking about something like, well, there are lots of ionic. Okay, let's talk about quartz versus diamond. They literally look similar, right? Obviously, one is silicon dioxide, the other is carbon. The silicon dioxide forms macro structures of quartz by sticking together different groups of silicon dioxide because of geological reasons I'm not going to explain. Whereas the diamond is literally carbon is bonding and holding hands with lots of other carbons, and they're all just holding on to each other. Whereas the quartz is just sticking. So yeah, big differences between those two. The only thing that's really similar between them is the giant. I think I'll stop it there. I have a few more things, a few more extra random things about my degree and other stuff. But maybe I'll put that in an extra video because it's not so specific to the GCSE. So thank you for watching. I hope that was helpful. Be kind to yourself, and yalla bye.